everyone and welcome to the internet. What we're going to be doing in today's lesson is having a look at radiation and the human body. So hopefully by the end of today's lesson you're going to be able to explain how we can both use radiation and some of the dangers of radiation as far as the human body is concerned. To start us off though, here are 4 questions based around our previous lesson. So have a go at answering these in your books for me. I'll give you about 3 minutes to have a go at this. Let's double check those answers then. So for question 1, what we were looking for is the structure of the atom. So you get 1 mark if you said there's a nucleus, a 2nd mark if you said that it's made up of protons and neutrons, 3rd mark for saying that the nucleus made of the protons and neutrons is surrounded by electrons, and your final mark for saying that those electrons are arranged in shells, or you may have described them as orbitals. Question 2, then an electron has been removed from the atom for our mark. Question 3, our absorption spectrum shows the frequencies of radiation that are absorbed by an atom when excited electrons are moved to those higher energy levels. And finally, question 4, it's to identify elements. So I think that's a total of 7 today, so add up your scores out of 7. The first thing we're going to be looking at today then is the sources of background radiation. And when we talk about background radiation, we're referring to the sources of radiation that you're exposed to all the time. So to start us off then, let's see if you can write me a list in your books of any sources of background radiation, so sources of radiation that you're exposed to all the time in your everyday life. And then once you've done that, rank those in order of the amount of radiation they expose you to. So next to the one that you think gives you the highest exposure to background radiation, put a number 1 and work your way down to however many you've got. So I'm going to give you a couple of minutes to have a go. So the first thing I'd suggest you do is just jot down that reminder of what we mean by that phrase background radiation. So whenever we see the phrase background radiation, what we're referring to is the source of radiation that you're exposed to all the time in your everyday life. So jot down that sentence at the bottom first of all. What we can then see in our pie chart in the center of the screen then are all the typical sources of background radiation that we're all exposed to day in, day out. Now, if we have a look at this, then half of that pie chart is actually designated to radon gas. Now, radon is a gas that's released by certain types of rocks, and we're exposed to this all the time in our everyday lives. That equates to about half of the background radiation. Then if we have a look at the next most common one, then we can see that we're actually coming into the artificial sources. But if we break that down into what those artificial sources are, then we can see medical uses is 14%. Now, so that would be all of your x-rays and so forth. But also at 14%, we can see ground and buildings is that same percentage there. So number 1, radon gas. Joint number 2, we've got medical uses, the ground and buildings. Then in our third place, we've got food and drink, which is 11.5%. Fourth place is cosmic rays. And then we come down to these other ones, and the ones you may have thought are quite high. So things like nuclear weapons tests that have occurred around the world, only 0.2%. And nuclear power stations, including any accidents that have occurred, that's only 0.1%. So they're actually a really tiny amount of the background radiation. The vast majority of it is coming from this radon gas, and then things like the ground itself, the buildings that we are surrounded by, and medical uses, plus your food and drink. So what I'd suggest you do is you don't have to copy the pie chart, but you can just put a bullet point list of these different sources of background radiation. And if you want to write down the percentage next to them as well, by all means, feel free. I'll leave this up for another couple of minutes so you've got a chance to write down any of the bits of information that you see fit. One of the things that's really important to do in this topic is to get our key terminology right. And I have actually seen questions in the past where you can pick up a couple of marks for definitions of keywords. Two of the common ones that people mix up are on the screen here: contamination and irradiation. When we're talking about contamination, then this is something that's going to occur when a radioactive material is taken inside the body or is onto the skin. Now, this means that we're coming into contact with this material and it's either being taken into our body or onto our skin. So we become contaminated with it. And if this is internal contamination, so if you've swallowed a load of radioactive material for some reason unknown to yourself, then we can't remove that. So that is pretty problematic. And we obviously saw a case of that not too long ago with the Russian spy who was in London having a lovely cup of tea at one of the hotels, and someone actually put some radioactive material within that tea and the bloke died. Because once you've actually consumed it, the radiation is in your body, you can't remove it. Irradiation then, our second term, this is when we've got radioactive material outside your body. And this is where the radiation can then travel into your body. And we looked earlier on in this topic about how different radiation penetrates through different materials. So contamination is inside the body or on the skin. Irradiation is outside the body. So make sure you've got those two key terms written down and you know the difference between them. So next thing to have a go at then is see if you can write down any of the problems of radiation entering the human body. Hopefully what we've got as our answer here then is that we pointed out that if radiation enters the body, then it can actually damage the DNA inside those living cells. And if we damage the DNA inside our living cells, that can lead to cancer. So what we actually need to do is try to avoid getting large amounts of radiation into our body. Because as soon as we've introduced the radiation, then we're at risk of damaging the DNA inside our cells, and that increases your risk of cancers. Now, it's not a case of every time you come into contact with something that is radioactive, then you're doomed to be covered with cancer within a week. Basically, when we're talking about these radioactive materials, they are a hazard. But the risk of cancer as a result of your normal exposure is actually low. So this is why we still send you for an X-ray if you've broken a bone or suspected to have broken a bone. Because finding out if that bone is broken and therefore knowing the best course of treatment, the benefit of that far outweighs the risk of that low dose of radiation exposure. Because from that single X-ray, it's highly unlikely that you would then develop cancer. Because what we actually find is that your body is actually pretty impressive. And if you're exposed to only small doses of radiation, then any damage that's done by that radiation can be repaired by your body automatically. So your body has a whole range of these different systems whereby it checks to make sure everything is as it should be, and any problems it finds, it can then correct them. So it can either kill off certain cells or it can redo certain bits of code and so forth. So it's not a case of just being exposed to a very small amount of radiation is a death sentence. Instead, what we do is we're weighing up the benefit versus the risk. And this is why when you go for an X-ray, they do check to see what X-rays you've had recently, because it's all about reducing your exposure. And as long as your exposure is low, then your risk is low. What we need to think about now then are what we're actually going to be using radiation for. Now, we've got three key things that we actually use radiation for. The first one is as something called a medical tracer. For a medical tracer, what we actually do is we take a radioactive isotope, and depending on what it is we're trying to work out, then you would either have it injected, you'd inhale it, or you'd swallow it. And obviously the method of its administration is going to be determined by what we're looking for. So if we wanted to know how your blood was flowing around your body, then we'd inject it into your bloodstream. If we wanted to know about how your lungs were working, then you'd inhale it. If we wanted to know about your digestive system, you'd swallow it. Once you've actually done that, the next thing that we do is we use a special bit of equipment called a gamma camera, and we then pass that over the body, the region we're looking at, and what it does is it detects the radiation, because the radioactive isotope that you have taken into your body is then going to be emitting this gamma radiation, which is able to pass out through your skin, because as we saw in our previous lesson, gamma is the most penetrating. It's picked up by the gamma camera, and then on a screen we can see where any problems are. So if you'd swallowed one of these medical tracers to look at your digestive system and there was a blockage in your intestine, what we'd see on the screen is the fact that there would be this increased amount of gamma radiation in one region of your intestine and then pretty much nothing after that point. So that means we can identify exactly where the blockage is without having to cut you open first. And that's always a good thing, because no one really wants to have their entire abdomen cut open and then a surgeon searching through all the meters of their intestine to find the problem. That's not great in terms of minimising your risk of infection. By using a medical tracer, we can identify exactly where the issue is and then have a much more surgical strike for it. Second is sterilisation. Now, what we find in terms of medical equipment is not everything is great to heat up. If we think about all the different implements that we use in medicine, sure, some are metal, so things like scalpels and so on, they're fine. You can heat those up to very high temperatures to kill any bacteria on the surface. But we also use a large amount of things like tiny plastic tubes. Now, if we heat up plastic tubes, we don't so much have a plastic tube anymore as a plastic blob. Now, that's not going to do very much in terms of medical procedure. But we still need to sterilise it. So what we can actually do is use gamma rays, expose the medical equipment to these gamma rays, and kill off any bacteria present on the surface. So these are our first two: medical tracers, sterilisation. Jot those down if you've not already got them. Before we go on to our third use of radiation, one thing that we've got to be really careful of is that the radiographer, who's the person in the hospital that deals with all the radioactive material, they've got to choose the isotope that they're going to give you to ingest or inject really carefully. See if you can suggest why that is. Hopefully what we picked out is that we've got a couple of key things here. Firstly, we need to think about the half-life. Now, half-life, if you remember, is the time it takes for half of the radioactive nuclei to actually decay. If we pick an isotope where the half-life is too short, then our tracer will have decayed before the gamma camera is actually used to detect it. That's a problem, because you've just taken something into your body, but you then won't be able to see anything. So, pretty useless. If the half-life is too long, then our tracer is going to be emitting radiation over a really long period, and that means we're going to be exposing that poor person to a large amount of radiation, and that's going to increase the risk of cancer. Again, not a good thing to do when we're treating people. So we want something where the half-life is just right. Not too short, not too long. It's one of those Goldilocks moments here where it's just the right length of time. And the one that we tend to use here is a material called technetium-99, and that's because it's got a half-life of about 6 hours. So plenty of time for us to actually use our gamma camera to detect it, but not too long to increase the risk of cancer. The other advantage that we've got of our technetium-99 is that it's actually absorbed by a wide range of organs, which means it's going to give us the clear pictures that we need. The final thing we need to consider when selecting a medical tracer is to make sure that we're not selecting something that only emits alpha particles, because as we saw previously, they're the least penetrating. They're stopped by mere paper. So if we ingest alpha particles, then they're not going anywhere. They're going to be absorbed by all of those cells immediately surrounding. Now that's going to be really bad news. We need something that's able to pass out of the body to our gamma camera. So we tend to use something that emits gamma radiation, hence we're using a gamma camera. The third and final use that we're going to look at is a gamma knife. Now, a gamma knife is a piece of equipment that we're going to use in order to treat cancer. I've given you a picture of it in the bottom right there, and the example we've got is for a brain tumour, and we can see the tumour is that red circle in the middle of the brain there. Now, the big advantage about using a gamma knife to treat cancer is that we're not having to cut into the body. So if we're thinking about something like our brain tumour as the example, it's not generally a good idea to cut into someone's brain and go poking around trying to remove tumour unless absolutely necessary. If we've got alternative means, it's far better, because as soon as we obviously cut someone's skull open and then start poking and prodding and pulling out bits of their brain, it can cause serious damage. So we like to avoid that where possible. In terms of what a gamma knife is, it's quite simply a movable source of gamma radiation. So you lie in this big machine and then this gamma source is going to move around the source of your tumour basically. Now what we do there is we're going to concentrate it on the tumour itself. So it's always going to be focused on those tumour cells, but we don't just stick it above one point of your head. If we left it in just one position on the outside of your body, just aiming at the tumour, then all of those cells on the run through your head, through your brain to the tumour itself, are also going to be exposed to a huge dose of radiation. Now the whole purpose of this is to expose the cancer cells to a high enough dose of radiation to kill them. So normal body cells exposed to that same dose would also die. That would be bad. So by having this movable source, what we're doing is keeping it focused on the tumour, but by moving it around the rest of the body, it means that the healthy cells get a much lower dose, so they won't be killed, but the tumour is going to get a high enough dose to kill it off. So this allows us to kill off those tumour cells without slicing and dicing into the body. So make sure we've got those couple of points down about how a gamma knife works. You don't need to worry about copying the diagram unless, of course, you really want to. So final thing for today then are the plenary questions. So those of you with target grades up to a grade 5, it's the 2 columns on the left. Those of you with target grades over a grade 5, it's the 2 columns on the right. So I'm going to leave these up for about another 3 minutes today, but as always, if you need longer, hit pause on the video and take as long as you need to answer those properly in your books.